Yeah, good morning everyone. This is Shravya. So today we are going to discuss about random variables, types of random variables, conditioning, different laws, types of distributions and many more. So let's start with the session. Hope you'll enjoy. So in the last session we discussed about random variables, right? Can someone respond what is a random variable in the chat? Am I audible?
Yeah, you're audible.
Can someone respond in chat what is a random variable? It was discussed each value. We will be considering all those x which satisfy g of x equal to y and add those probabilities to get probability that y equal to y. So we got sigma x such that g of x equal to y, px of x here. And in the next step, it will be sigma y, sigma x give x such that g of x equal to y, y into px of x. Now just y equal to g of x, so substituting here. And now sigma y, sigma x such that g of x equal to y, g of x into px of x. Now first we are adding all the x's for x for which g of x is y, and then adding all the y. That means we are basically considering all the possible values of x. So just replace it by summation x g of x into px of x. So this is how we got this formula. Yeah, you can apply it for any function of random variable x. Look at properties of variance and expected value. For any random variable x, variance is greater than or equal to 0. The square root of variance is called standard deviation and is denoted by sigma. I mentioned it in previous slide also. If y is equals to ax plus b, where a and b are given scalars, then e of y equal to a e of x plus b, variance of y equal to a square variance of x, and sigma y equal to a into sigma x. Just it will be useful for some of the functions of the form ax plus b. You can directly calculate expected value, and variance will be just simple to derive. You can derive it yourself. Variance of y will be a square into variance of x. Just apply square root, you will get the expression for relation between y and x for the standard deviations. So there is expression for variance in terms of moments. So generally that variance by its definition to calculate is not so easy. So we will generally calculate variance using this formula. Variance of x is equals to e of x square minus e of x whole square. This is a useful formula. Everyone do remember. Generally variance we will be calculating using this formula in any problem in most of the cases. So do remember this. So this is the point to be noted. Unless g of x is a linear function, it is not generally true that e of g of x is equals to g of e of x. Try deriving it yourself, but it is not generally true for any function. So now let us look at an example. If x is a discrete uniform random variable that takes integer values starting from a to b, find the PMF of x and also calculate the expected value and the variance of the random variable x. So given that x is a discrete uniform random variable and takes values from a to b, that means probability of occurrence of any value, any numerical value between a and b is same. From a to b, there are how many values are there? It will be b minus of a minus 1, right? So total number of integers which it can take is b minus of a plus 1. And all of them are taken with equal probability. So let's assume that probability as b. Then by normalization, the total probability should be 1. So 1 is equals to p into b minus a plus 1. So this will imply p equal to 1 by b minus a plus 1. So each integer can be taken with this probability. So PMF of x will be given like this. It will be p for x equal to a plus 1 till b, 0 otherwise. And expected value of x by definition, as it can take from a to b, x equal to a to b, x into px of x, which is equal to px of x is same for all the values from a to b. So take it outside common as common, p into sigma x equal to a to b x. It's just a calculation part. you need to calculate sum from A to B. Just calculate sum of natural numbers till B and then subtract the sum of natural numbers till A minus 1. Then finally, you'll get it as A plus B by 2 on simplification. And for variance, apply the formula which we saw in the previous slide, E of x square minus E of x whole square. Yeah, like you know the difference, right? E of x square is sigma x square into px of x. E of x whole square is, we'll calculate E of x and then take its square. So it will be sigma x equal to a to b x square into px of x minus this square of the expected value a plus b by 2 whole square. Again, just a simple calculation. You'll get it as b minus a into b minus a plus 2 by 12. So for if you take a discrete uniform random variable which has uniform probability from a to b, then E of x is will be a plus b by 2 and variance will be b minus a into b minus a plus 2 by 12. Now try yourself, calculate the PDF expected value and the variance if the random variable is continuous uniform. So similarly for the continuous case also you try calculating expected value, variance and PDF if the random variable is uniform. Is everything clear? Coin tossing. Consider two independent coin tosses for a biased coin with probability 0.75 for a head, and let x be the random variable that denote the number of heads obtained. Then find the mean and variance for x. If there is, we are tossing a biased coin for 2 times and given the probability of head to be 0.75 and consider random variable as number of heads. Then find mean and variance of x. Try this question and respond with your answers in chat. So let us look at the solution. We got many answers. Let us calculate the PMF. If the random variable equal to 0, that means number of heads are 0. So both are tails. Probability for a tail is 1 by 4. So 1 by 4 into 1 by 4, 1 by 4 whole square. If k is equals to 1, that means we have one head. So it will be head tail or tail head. So two possibilities. So 2 into, for the tail, probability is 1 by 4. For head, 3 by 4. So 2 times 1 by 4 into 3 by 4. If k equal to 2, we have both to be heads. Probability of head is 3 by 4. So 3 by 4 whole square. Now just apply the formula which we discussed for E of x. Sigma x into px of x. So just 0 into this 1 by 4 whole square, 1 into this 3 by 8 and 2 into 3 by 4 whole square. It will be 1.5. And for variance, you can for head 3 by 4. Calculate so 2 times 1 square. And then calculate variance using E of x square minus E of x whole square. Variance will come out to be 3 by 8. Let's go to next question. Lazy but sincere. Anjali is a lazy but a sincere girl. So she don't want to miss a class. But being lazy, she sleeps till the last moment. So her daily routine would be wake up and rush to class every day. Every day she waits at the lift. Let the random variable t denote the time Anjali waits for the lift to arrive. Suppose the longest that Anjali needs to wait is 2 minutes. The PDF of t is given by f of t is equals to t for 0 less than t less than equal to 1, 2 minus t for 1 to 2, 0. Okay, if he goes by walk, then he goes with a speed of 5 km per hour. Then the time taken will be 2 by 5 hours. Time taken will be 2 by 5 hours, and that happens with the probability 0.6. So probability will be 0.6 if t equal to 0.4 hours, and he goes by cycle, then speed is 20. Then he takes the time of distance by speed, which is 2 by 20, that is 0.1 hours. So if time is 0.1 hours, so now he goes by bicycle with a probability of 0.4. So 0.4 if t equal to 0.1 hours. This is the PMF of time. Just calculate the time by distance and speed, and then put its probability there. Now let us calculate expected value of time, which is again just apply the definition 0.6, which is probability into time 0.4 plus again probability 0.4 into time is 0.1, that will be 0.28. Someone might ask, can we do by taking expected value of speed and then divide 2 km by the expected value of speed? Someone may think like this also now. Why can't we, already given information is on speed, right? So why can't we first calculate the expected value of speed and then divide 2 by that expected value of speed and find the expected value of time now? So let's try doing that way once. Let's calculate E of V. E of V is nothing but 0.5, which is probability into speed, that is 5. 0.5 is probability of walk into speed for walk, and plus 0.4 into 20, which is 11. Now expected value of time, if you want to find by distance by speed, it will be 2 by 11, which is 0.18, which is not same as which we calculated from the actual method. So this is a best example to tell that E of g of x is not equal to g of e of x. Here what we are doing, we know here we are in E of g of x, we found by the first usual method, and g of e of x, first we are finding expected value of speed, then we are substituting in the distance by speed and finding expected value, trying to find expected value of v, but that is not correct because this is not a linear function. So E of t is not is equal to E of 2 by V, but it is not equal to 2 by E of V. So this gives an example for E of G of X is not equal to G of E of X. So basically you need to make sure that you are calculating the expected value using PMF or PDF of the required random variable. So here what we require is the expected value of time. So first you need to calculate the PMF of time and do the required thing. So make sure you do the problem using the required random variable. Okay. Is it clear till here? So now let us look at cumulative distributive functions. The CDF of a random variable x is denoted by fx and provides the probability p of x less than or equal to x. So CDF is defined to be the probability that probability for x less than or equal to x. That is the definition. For discrete and continuous, let us look at how can we find. For discrete, this CDF is denoted by capital Fx. Like don't get confused for CDF and PDF. That is denoted by small f. Here it is denoted by capital F. For discrete, Fx will be probability that x less than or equal to x. That means we need to add probabilities of all the values which are less than or equal to x. So sigma k less than or equal to x, px of k, adding all those. And for continuous, it will be fx will be p of x less than or equal to x, which is we want probability in the interval minus infinity to x, right? Because every value less than or equal to x, we want to find a probability. So integral minus infinity to x, fx of k dk. For discrete, this fx like CDF is a constant piecewise staircase form. It looks like that if you plot it. And for continuous, it is continuously varying form. Probability that x equal to k by using the fx of x, then now fx probability of that x equal to k, we can find it by finding probability that x less than or equal to k, that probability till k minus probability till k minus 1. That gives probability of k, right? Probability that x equal to k. It gives probability, right? Because we are considering till k and then subtracting the k till k minus 1. Then we'll get the probability that x equal to k. So probability that x less than or equal to k is nothing but it is fx of k by definition. And again, probability that x less than or equal to k minus 1 is nothing but fx of k minus 1. So we can find CDF from the PMF by summation, and we can find the PMF by subtracting this two consecutive CDFs. We can find the PMF. So here we are doing adding, here we are doing subtracting. Similarly, if you consider continuous random variable and given PDF, then here we are doing for discrete case, we are adding and finding CDF. So for continuous case, just we will be replacing that summation by integration. We will be integrating and finding. And PDF, for finding PMF, we were doing subtraction. Here for finding PDF, we will be differentiating. Just addition, integration, subtraction, differentiation. That's the only difference. So fx of x is by definition minus infinity to x, fx of k dk. And here again by differentiation, dfx of x by dx, we can find the PDF. For discrete, you need to add and subtract. For continuous, you need to integrate and differentiate. That's it. Question: maximum of several random variables. Okay, you are allowed to take a certain test 3 times and your final score will be the maximum of these 3. Thus, x equal to max of x1, x2, x3, where xi is the score in the ith test and x is the final score. Each test score can vary, can be any integer from 1 to 10 with equal probability. What is the PMF of the final score? So you are allowed to take a test 3 times and the final score will be maximum among the 3. Like if x1, x2, x3 are the 3 scores, maximum among those 3 will be the final score. Now each of the x1, x2, x3 can take any value from 1 to 10 with equal probability. So you need to find the PMF of the final score. Here, try applying find PMF from that by what we discussed. Try let's look at the solution. So we can calculate the PMF indirectly. We will first compute the CDF fx of k and then obtain the PMF px of k is equals to fx of k minus fx of k minus 1. So we'll apply the concept which we saw in the previous slide. It is by finding first CDF and then doing fx of k minus fx of k minus 1 to find px of k. Now fx of k, that is nothing but by definition p of x less than or equal to k. That means maximum score should be less than or equal to k. Maximum is nothing but maximum among x1, x2, x3. So all the 3 should be less than or equal to k for that maximum to be less than or equal to k. So probability that x1 less than or equal to k into probability that x2 less than or equal to k into probability that x3 less than or equal to k, as 3 are like independent ones. So for probability that x1 less than or equal to k, it is k by 10 because k values can occur among 10. So it will be k by 10. Similarly for remaining 2. So it will be k by 10 whole cube. So probability that x less than or equal to k is k by 10 whole cube, which is fx of k. Now fx of k minus 1 will be k minus 1 whole cube by 10 cube. So now we can find px of k, which is PMF by subtracting fx of k minus 1 from fx of k, which will be k cube minus k minus 1 whole cube by 10 cube. Okay. This is a good application to find PMF from the given CDF. So is it clear till here? You can respond if it is clear. You can respond if it is clear. So now let us look at multiple random variables. You can respond if it is clear. First, let us look for discrete ones. Joint PMF for two discrete random variables x and y is defined by pxy of x comma y, which is equal to p of x equal to x, comma capital Y equal to y. So now let us look at for the multiple random variables. You can respond if it is clear. Defining PMF, we told it is probability that random. Let us look for discrete ones. PMF of x. Joint PMF for two discrete random variables x and y is defined by pxy of x comma y, which is equal to p of x equal to x, comma capital Y equal to y. Joint PMF of x and y. Now let us look at for multiple random variables. You can respond if it is clear. Defining PMF, we told it is probability that x comma y. Let us look for discrete ones. PMF of x. Joint PMF for two discrete random variables x and y is defined by pxy of x comma y, which is equal to p of x equal to x, comma capital Y equal to y. Joint PMF of x and y. Now let us look at for multiple random variables. You can respond if it is clear. Defining PMF, we told it is probability that let us look for discrete ones. PMF of x. Joint PMF for two discrete random variables x and y is defined by pxy of x comma y, which is equal to p of x equal to x, comma capital Y equal to y. Joint PMF of x and y. Now let us look at given by px of x is equals to p of x equal to x, which is equal to sigma y, p of x equal to x, comma y equal to y, sigma y, pxy of x comma y. So normal PMFs are of x and y are referred to as marginal PMFs, and these can be found from the given joint PMF. Let's see how. If we want to find px, that means we want to find p of x equal to x. Now let us say this is an event. P of x equal to x is an event. Now so to find the probability of any event, we need to consider all the pairs x comma y which satisfy that. So we need to add probabilities using joint PMF considering pairs x comma y such that x equal to x and y can be any value in the range. So that gives summation y pxy of x comma y. X will be x and y will vary over entire range. So that gives the marginal PMF of x. Similarly, for marginal PMF of y, sigma x pxy of x comma y. Y will be y and x can vary over entire range. So this way you can find the marginal PMF. So let us look at an example. A fair coin is tossed 3 times. Let x be the value of a random variable that takes the value 0. The first toss is a tail, and that takes the value 1. The first toss is a head. Also let y be the random variable that defines the total number of heads in the 3 tosses. Determine the joint PMF of x and y. So given two random variables, x which is 1 when it is a head and 0 when it is a tail, and y is denoting the total number of heads in the 3 tosses. So we need to determine the joint PMF. So let h denote the event that a head appears and t the event that a tail appears on a toss. Each of the sample points are equally likely to be obtained. Now our experiment is 3 tosses of a coin. So each toss can be a head or a tail. So total there are 8 possible outcomes. Each of them are equally likely. Now x can take values 0 and 1 as per how it is defined, and y can vary from 0 to 3 because y denotes number of hits and there are 3 tosses, so y can be anything 0, 1, 2 or 3. The joint PMF of x and y can be constructed as follows. So let's see. This table below indicates the combined PMF. Let's look at for some. I will explain for some of them. If x equal to 0 and y equal to 0, that means you have number of heads to be 0, and y equal to 0 means number of x equal to 0 is nothing but first one is a tail, and y equal to 0 is that number of heads are 0. Number of heads are 0. So each of them must be a tail. So that t only one possibility among the 8. So 1 by 8. If x equal to 1 and y equal to 0, then first one is a head and y equal to 0 implies number of heads are 0. Both are not possible at a time now. So probability should be 0. Similarly, for any pair x and y, you can calculate probability similarly and construct the joint PMF in this way. Now let us look at multiple random variables for continuous ones. So joint PDF for two continuous random variables x and y. The joint PDF xy satisfy p of x comma y belongs to b is equals to integral x comma y belonging to b fxy of x comma y dx dy. So generally, if we have only one random variable, to find the probability that random variable belongs to some interval, we will be integrating given PDF over that interval and finding the probability. So here, as we have two random variables, to find the probability that x comma y belongs to b, we need to double integrate for x and y with the given interval and for the joint PDF and find the probability. The only difference is there we will be integrating once. Here we are integrating twice. One integration on x and y. Double integration we will be performing to find the probability. So in detail, if probability that a less than or equal to x less than or equal to b and y lies between c and d, then to find probability for this, you need to integrate integral a to b, integral c to b, fxy of x comma y dx dy, where a is the set of all pairs xy that have a certain property. So to find probability for this given that x and y lies in the given intervals, you need to integrate in those intervals and find the probability. Now again, by normalization, if you integrate on xy over entire range minus infinity to infinity, then probability should be 1. fx and fy are referred as marginal PDFs and are given by fx of x is equals to p of x equal to x, which is equal to integral minus infinity to infinity p of x equal to x comma y equal to y, which is equals to integral minus infinity to infinity fxy of x comma y. So again, here also fx, similarly how we told that px and py are marginal PMFs, fx and fy are also marginal PDFs, and these can be calculated again from this joint PDF. Again, here when fx, if we want to calculate fx of x, that is probability that so you need to there we for calculating px of x, we did the summation over entire y, right? So here we need to integrate the over entire y, over the entire range minus infinity to infinity. Joint PDF, we need to integrate. That is minus infinity to infinity fxy of x comma y dy. There we will be summing. Here we are integrating. That's it. Let us look at some more things regarding multiple random variables. If z equal to g of x comma y defines another random variable, its PMF is calculated as pz of z is equals to sigma x comma y such that g of x comma y is equals to z pxy of x comma y. Okay, if we assume z to be some random variable which is a function of random variables x and y, then to calculate PMF of z, that is capital Z equal to small, probability that capital Z equal to small z, that means we need to consider all the values of x comma y and add the probabilities using joint PMF such that those all values satisfy g of x comma y is equals to z. Add all such probabilities, then you will get pz of z. That is PMF of random variable Z. Now E of G of x comma y is sigma xy, G of x comma y, Pxy of xy. Again, E of G of x, we defined it as sigma G of x into Px of x, right? There G of x, here G of x comma y. So replace G of x by G of x comma y, and probability like normal PMF by joint PMF. Just replacing that, you'll get the uh, equation. Again, for continuous, it's the similar thing. Integral minus infinity to infinity, like 2 times g of x comma y, fxy, x comma y, dx dy. Just if you derive the formula for the discrete ones, just replacing summation by integration and probabilities by joint PMF dx dy, you will get the same. Again, you can easily get the equations. Uh, So E of next one, E of ax plus by is equals to a into E of x plus b into E of y. Again, the similar thing, you can derive it easily. You can even generalize the above for n number of random variables as well. Actually, all the above things, multiple random joint PMFs which we discussed for the two random variables, you can generalize everything for more than two. You can try yourself. Even this above expression E of ax plus by also you can generalize for the n number of random variables. Like if you write E of uh, a1 x1 plus a2 x2 plus a3 x3 so on, then you can write it as a1 into E of x1 plus a2 into E of x2. Like that you can generalize for n number of random variables as well. Conditioning of a random variable. Is it clear till here? Is it clear? Conditioning of a random variable. For a discrete random variable x, the conditional PMF condition on a particular event A with P of A greater than or equal to 0 is given by P x given A of x is equals to P of x equal to x given A, which is equal to P of x equal to x intersection A by P of A. Normally while discussing probability, we define conditional probability to be uh, P of B by A equal to P of B intersection A by P of A, right? So, like, if B is some event x equal to x, then just replace it by x equal to x. You'll get the required one for this discrete random variable. Just similar formula, just replace that event by x equal to x. You'll get it to be P of x equal to x intersection A by P of A. This is nothing but conditional PMF of x, which is Px given A. Since the event x equal to x intersection A are disjoint for different values of x, their union is A, and therefore P of A is equals to sigma x P of capital X equal to x intersection A. So if we take different events x equal to x intersection A, so adding all those will be covering the entire A. X equal to x intersection A. Each x equal to x intersection A will cover some part of A. By taking all such x's and for a continuous random variable, the conditional PDF conditioned on a particular event A with P of A greater than or equal to 0 is given by a function fx given A that satisfies P of x belongs to B given A is equals to integral B fx given A of x dx. So if we have a continuous random variable, and we are given with the conditional PDF, and we need to calculate that x belongs to b given a probability. Normally, if you want to find probability that x belongs to b, then we integrate b. We do the integration for the given PDF over the interval b. So here the only difference is we are finding x belongs to b given a occurs. So we need to integrate the over the interval b for the conditional PDF. Just replace the normal PDF by the conditional PDF, as it is the conditional probability. That's the only change in the formula. There p of x belongs to b is integral b fx of x dx. Here p of x belongs to b given a is integral b fx given a of x dx. Just as we are finding conditional probability, use the conditional PDF. That's it. So when we condition on x belonging to a subset A of the real line such that p of x belongs to A is greater than or equal to 0, we then have p of x belong to B given x belong to A is equals to p of x belong to B and x belong to A upon p of x belong to A, which is integral A intersection B fx of x dx upon p of x belongs to A. Then the PMF is given by fx given a of x is equals to fx of x upon px belongs to a if x belongs to a, 0 otherwise. So here we are trying to relate conditional PDF with the PDF of x. So just by using the definition in the previous slide, and here we are p of x belong to b and p of x belong to b and x belong to a. That means we are basically finding probability in the interval A intersection B. So integrate fx of x dx over the interval A intersection B and just simplify. Then we will get fx given A of x as fx of x by p of x belong to A. So this is how we can relate conditional PDF of x with PDF of x. So now let us look how can we find expected values. Let x be a discrete or continuous random variable of an experiment. Given that A has occurred, then E of x given A is sigma x, x into P of x given A of x. Again, similarly for continuous. So E of x, by definition, we write sigma x into Px of x. Like normally, we will be writing sigma x into Px of x, right? Now here we are finding E of x given A. So replace the probability by P of x given A. If there is E of x, we'll be using P of x. If E of x given A, then use the conditional PMF P of x given A. That's how we get this. And for conditional, for continuous, we use integration and replace conditional PMF by conditional PDF dx. So it will be integral minus infinity to infinity x into fx given a of x dx. Just the same thing, replace normal things by the continuous things to find this continuous ones. For a function g of x, the conditioning is given by e of g of x given a is equals to sigma x g of x into p of x given a of x. Again the same. Just apply expected value rule, replace x by g of x, and everything remains the same in the previous expression. So e of g of x given a, which is sigma x g of x into p of x given a. And again for continuous, just replace sigma by integral and conditional PMF by conditional PDF into dx. You'll get the expression. So let's look at an example to understand better. Let x be a random variable denoting the number on the top of a die when it is rolled, and a be the event that the die shows an even number. Then find the PMF. So the PMF, we need to find a conditional PMF of x. Here, what's the random variable? Random variable is the number denoting on the top of the die when it is rolled. And event is that die shows an even number. So we need to find probability that for finding the PMF, we need to find probability that x equal to x given x belongs to 2, 4, 6. So by definition, we can write it as probability of x equal to x intersection x is even by probability that role is even. So this is everything by definition. Now, now let us substitute different values and see. If let us say x is odd, let's take the value 1. Probability that x is 1. That means on the top of the die, the number is 1 and x is even. On the top of the die, number is 1. That means it is odd. So it is not even. So this probability of this occurrence is 0. So whenever we take any value of x which is odd, probability will be 0. And when we take x to be some even value, let's say 2. Probability that x equal to 2 and x is even. What's the probability that x equal to 2? It is 1 by 6, right? And probability that roll is even. Even in the sense we can take 2 or 4 or 6. Probability among the 6. Among the 1 to 6, we can take 2, 4, 6. So this probability will be 1 by 2. So it will be 1 by 6 upon 1 by 2 for x equal to 2, 4, 6. So it comes out to be 1 by 3 if x is even, 0 otherwise. Okay. Conditioning a random variable on another. Let x and y be two discrete or continuous random variable associated with the same experiment. Then the conditional PMF P of x given y of x given y is equals to P of x equal to x given y equal to y, which is P of x equal to x and y equal to y upon P of y equal to y, which is equal to P of x comma y of x comma y by P y of y. So now we are conditioning a random. Previously, we conditioned a random variable on an event. Now we are conditioning random variable on another random variable. So the difference is we are replacing that event by the let us assume that in the previous case, if we assume that event A to be y equal to y and replace here, we'll get the required things. So again, P of x equal to x given y equal to y. Just by definition, we can write P of x equal to x and y equal to y by P of y equal to y. And x equal to x and y equal to y, we can find from the joint PMF, which is Pxy of x comma y upon Py of y. So to find the conditional PMF of x given y occurs is equals to joint PMF of x comma y upon Py of y. So similarly for the case of continuous, conditional PDF of x given y will be equal to joint PDF of x and y upon Py of y. Just replace PMFs by PDFs. And normalization ensures again sum of summation x px given y of x will be 1. And for continuous integration from minus infinity to infinity, it should be 1. Now multiplication rule is given by, so to find this, just cross multiply Py of y. You will get, this rule can be used to find joint PMF from the conditional PMF of x given y. So just cross multiplying Py of y, you will get it to be Px comma y of x comma y, which is equal to Py of y into Px given y of x. So joint PMF of x comma y will be equal to Py of y into conditional PMF of x given y. So similarly for PDFs, joint PDF will be Fy of y into conditional PDF of x given y. And now to find the total probability Px of x. So now while discussing joint PMFs, we discussed how to find marginal PMF from the joint PMF, right? If we want to find Px of x from Pxy of x comma y, we did the summation over the entire range of y. So again, you do the same here. To find Px of x, we need to do the sigma y of Pxy of x comma y. But from the multiplication rule, this pxy of x comma y is py of y into px given of x given y. So just summation y for this will give px of x. And similarly, again for the continuous, f to find fx of x, which is marginal PDF, we can find it from the joint PDF, which can be written in terms of conditional PDF using multiplication rule and just integrating. So let us look at something important, total expectation theorem. So before that, let's look at how to write E of x given y equal to y. We wrote, okay, E of x we will be writing as sigma x into px of x. Here again it is replaced by x given y. So E of x given y will be same x into replace px of x by px given y. So it will be sigma x of x into p of x given y. Again for continuous, just replace summation by integration and probability by PDF dx. You'll get the required one. Now let us look at total expectation theorem. The total expectation theorem is given by E of x is equals to sigma y py of y into E of x given y equal to y. So to find the expected value of x, take all the cases, separate cases for different values of y, find the expected value of x for each case and multiply it by the probability with which that y can occur. This is the same logic as like total probability theorem. Similar logic. There we would find probabilities. Here we are finding expected value. That's the only difference. And similar expression can be written for continuous ones. So we have the following useful version of the total probability theorem. Let A1, A2, so on, A and B disjoint events that form a partition of the sample space and assume that P of AI is greater than 0 for all I. Then E of x is equals to sigma I P of AI into E of x given AI. So just assume each y equal to y to be an different event. Consider those events to be A1, A2, A3, so on, disjoint events. And assume that all A1, A2, A3, so on, AN to be disjoint events. And now just modify the expression a little bit. It will be sigma I P of AI into E of x given AI. Calculate the expected value for each of the events occurs and probability that event occurs, and sum all those to get the expected value of x. It's similar to total probability theorem, just we are finding expected values. Let's look at an example. Message is transmitted by a computer in Boston through a data network and are destined for New York with probability 0.5, for Chicago with probability 0.3, and for San Francisco with probability 0.2. The transit time of a message is random with mean 0.05 seconds. If it is destined for New York, 0.1 seconds for Chicago and 0.3 for San Francisco, then calculate the expected transit time for the message. This is something application of total expectation theorem. We are given expected values given that they are destined for New York, Chicago, and San Francisco, and we need to find the total expected time. And they also given the probabilities with which the messages will be transmitted for Boston, from Boston to New York, Chicago, and San Francisco. So just this is the direct application of total expectation theorem. We'll look at the solution. Applying total expectation theorem, we need to find the expected value that it is destined for New York, given expected value of transit time given it is destined for New York into probability of New York. Similarly for Chicago and for San Francisco. So what is the expected transit time given it is destined for New York? It is 0.05, right? So 0.05 into probability that it is destined for New York. probability is given as 0.5. So it is 0.5. And again, similarly, expected time given it is for Chicago is 0.1. So 0.1 into probability that it is destined for Chicago, that is 0.3. Similarly for the other one. So adding all this will get 0.115. So this is how application of total expectation theorem would be. Now let us look at law of iterated expectation. This law states that the expected value of a random variable is equal to sum of the expected values of the random variable conditioned on a second random variable. Mathematically, E of x given y is equals to E of x. So, like orally, I'll explain you how you'll get this. So, if you take E of x given y, E of x given y is nothing but a function of y. It varies for different values of y. So E of x given y1 is different. E of x given y2 is different. So for different values of y, E of x given y will be different. So E of x given y is nothing but a function of y. So now if you assume that to be some function g of y, let us assume E of x given y is a function of y which is some g of y. So it is nothing but E of g of y, right? Now we know the formula for E of g of x. It is sigma g of x into px of x. So here E of g of y is there. So sigma g of y into py of y. Here g of y is nothing but E of x given y. So what we get is something like this. It will be E of x given y into py of y sigma. Just we are applying for E of g of y, which is E of x given y. We assume g of y to be E of x given y and applied the formula of expected value. We'll get this expression. This is nothing but E of x. So that is how we get E of x given y to be equal to E of x. So we will look at an application. We start with a stick of length of L. We break it at a point which is chosen randomly and uniformly over its length and keep the piece that contains the left end of the stick. We repeat the same process on the stick that we are left with. What is the expected length of the stick that we are left with after breaking the stick twice? So you can try this question. This is nothing but application of law of iterated expectations. Assuming we need to here what we need to find what is required is expected length of the stick that we are left with after breaking the stick twice. From law of iterated expectations, what we find is E of x. So let us assume x to be a random variable which is denoting length, denoting the expected length of the stick after we break it twice. Okay, and assume y to be expected length after we break it once. So try to find E of x by applying E of x given y. Try it for 1 minute. Get a solution. So let y be the length of the stick after we break for the first time, and x be the length after the second time. Just like what I told, assume x to be random variable denoting the length of the stick after second time, and y to be the length after the first time. So now what we want to find is e of x. From law of iterated expectations, it is e of x given y. Now e of x given y is nothing but what is the expected value of length of stick after breaking for the second time, given after breaking for the first time length is y. Given it is y, then after breaking once more, expected value will be average value, which is y by 2. So it is y by 2, and this is nothing but e of y by 2. Now e of y is expected value of length after breaking for the first time. Given the length is L, so after breaking once, expected length will be L by 2. So L by 2 by 2, which is L by 4. So that is how we get it L by 4. Is it clear?
How are we getting L by 2? Can you repeat once?
The L by 2 part. Okay. Expected e of y. What is e of y? E of y is the length of expected length of the stick after we break for the first time. Initially, the length is L. So on average, if you break anywhere, like we can break anywhere, on average, what is the length we can expect? As the length is L, we will expect averagely, on average, it would be L by 2 only, right?
Okay, yeah. But
Yeah, okay. So let's go to the next one. Okay, now let us look at types of distributions. We'll discuss some distributions of discrete and continuous. For discrete ones, we will discuss Bernoulli, binomial, geometric, and Poisson distributions. And for continuous, we'll discuss exponential and normal. So let us discuss Bernoulli random variable. So let us consider the toss of a coin, and let p be the probability for a head and 1 minus p be the probability for a tail. So now Bernoulli random variable is nothing but any random variable which takes only two values, like yes or no kind of thing. Like in this case, if we assume random variable x to take value 1 if it is a head and 0 if it is a tail, this is nothing but a Bernoulli random variable. So not only here, in any case where there are only two outcomes, we can assume a Bernoulli random variable and apply. So its PMF is given by Px of x equal to P if x equal to 1, 1 minus P if x equal to 0 in this case. And mean and variance you can calculate by the known formula. First calculate E of x, then find variance using E of x square minus E of x whole square. You'll get mean to be P and variance to be P into 1 minus P. Its daily life applications include probabilistic situation with just two outcomes, such as the state of a telephone at any given time, either busy or not. A person may be sick or not with a particular disease. Just like only two possibilities. A person, if you consider a person, he may be sick or not. There are only two possibilities, right? So even if you take a coin toss, head or tail, only two possibilities. In such situations, you can apply Bernoulli random variable. Binomial random variable. Again, let us consider the toss of a coin. Having probability p for a head and 1 minus p for a tail. Let's say that a coin is tossed for the n times, and let x be the random variable denoting the number of heads in the n toss sequence. Now, x can be referred to as binomial random variable with parameters n and p. Its PMF is given by px of k, which is p of x equal to k, which is nck p par k into 1 minus p whole power n minus k. So we are having, we are performing n tosses and probability of head is p. So p of x equal to k, that means random variable value is k, which means number of heads in the n toss sequence should be k. That means we have k heads and n minus k tails. K heads means we can select any k tosses among the n tosses. So nck into k heads, each head can occur with probability p. So p bar k and n minus k tails. Each tail can occur with probability 1 minus p. So 1 minus p whole power n minus k. So this is involving some binomial terms and hence called as binomial random variable. So this is the PMF of binomial random variable. This PMF is symmetric around n by 2 if p equal to half. Otherwise, it is skewed towards 0 if p is less than 0.5, else towards n. And expected value of x for a binomial random variable will be np, and variance is np into 1 minus p. So you can try yourself finding u of x and variance of x. I'll give you a hint. Just you can assume each toss to be a separate random variable and try finding. If you proceed that way, you can find u of x and variance of x easily. Try yourself. This is a binomial random variable. Geometric random variable. Again, consider the toy cost. Again, have probability for a head, let it be p. And now geometric random variable is number of tosses for a head to come up for the first time. Its PMF is given by Px of k, which is equal to 1 minus p whole power k minus 1 into p for k equal to 1, 2, so on. So, geometric random variable, that is number of tosses for a head to come up for the first time. So, Px of k means probability that x equal to k. That means what's the probability that number of tosses for the head to come up for the first time is k. So we are performing k tosses and till k minus 1 all are tails and head comes for the first time at the kth toss, right? So we are having first k minus 1 tosses to be tails and kth toss to be head. So what's the probability for that event? It will be 1 minus p whole power k minus 1, since there are k minus 1 tosses, into p, probability for the head in the kth toss. So PMF will be 1 minus p whole power k minus 1 into p. More generally, we can interpret the geometric random variable as the repeated independent trials until the first success. So here, generally we can interpret it to be number of trials until the first success occurs. Here, that first success is the first head when it is coming. In this example, it is the head. In generally, it will be what's the number of trials until the first success. That can be considered as a geometric random variable. Mean is 1 by p and variance is 1 minus p by p square. For this geometric random variable. Again, you try yourself. To find this, you can apply total expectation theorem to find the expected value of geometric random variable. Try yourself. Poisson random variable and exponential. A Poisson random variable takes non-negative integer values and its PMF is given by Px of k, which is equal to e power minus lambda into lambda power k by k factorial, k equal to 0, 1, 2, so on. So, Poisson random variable has PMF which looks something like this. For a Poisson random variable, E of x is lambda and variance is also lambda. Just you can apply given definitions and find them easily only E of x and variance of x. You'll get them to be lambda and lambda. And one more important point to be noted. A Poisson PMF with parameter lambda is a good approximation for a binomial PMF with parameters n and p, provided lambda is equals to np, where n is very large and p is very small. So, where we can apply this Poisson PMF is that in case of binomial random variables which have large value of n and small value of p, then take lambda to be np, lambda value to be np, and apply Poisson PMF. So let's take some example like consider a city and number of car accidents to be a random variable. Now n will be very large because total number of cars in a city will be a large one, and p to be probability that a car is involved in an accident, that is very small. So in that case, if those both are given, then you can calculate NP value, take it to be lambda, and can apply Poisson random variable. So any binomial random variable which has large n and very small p, you can consider lambda to be NP and apply Poisson PMF. That's where you can apply Poisson. Exponential random variable. Now from here we will be discussing continuous distributions. An exponential random variable has a PDF of the form fx of x, which is equal to lambda e power minus lambda x for x greater than or equal to 0 and 0 for x less than 0. So this is how PDF of exponential random variable looks like. For exponential random variable, probability that x greater than or equal to a is integral a to infinity lambda e power minus lambda x dx, which is e power minus lambda a. So probability that x greater than or equal to a for an exponential random variable falls exponentially. So again, the variance mean is 1 by lambda for an exponential random variable, and variance is 1 by lambda square. You can find them easily. So here is an example. The time until a small meteorite first lands anywhere in Sahara Desert is modeled as an exponential random variable with a mean of 10 days. The time is currently midnight. What is the probability that a meteorite first lands sometime between 6 a.m. and 6 p.m. of the first day? So, given it is an exponential random variable and mean is given to be 10 days, we know that mean for an exponential random variable is 1 by lambda, which is given to be 10 days. That means lambda value is given for us. And we need to find probability between 6 a.m. and 6 p.m. of the first day. That means if we convert it into days, basically 1/4 of the day and 3/4 of the day. Between that, what's the probability that meteorites lands? Maybe you can try it for a minute. Ashwin, normal or Gaussian random variable? A continuous random variable is said to be normal or Gaussian if it has PDF of the form fx of x is equals to its mean is mu and variance is sigma square. So if x is a normal random variable with mean mu and variance sigma square, you can write y equal to ax plus b. It is also a normal random variable and its mean will be a mu plus b and variance will be a square sigma square. Now there is one special normal random variable which is the standard normal random variable whose mean is 0 and variance is 1. So just in the given form, substitute mean to be 1, mean to be 0 and variance to be 1. And also its CDF is of importance, which it is denoted by phi of y. Phi of y is nothing but CDF of standard normal random variable, which is probability that y is less than or equal to y by definition. That will be just substitute sigma to be 1 and mu to be 0 and integrate from minus infinity to y to find the CDF, which will be 1 by root 2 pi integral minus infinity to y e power minus t square by 2 dt. So more about standard normal random variable. Let x be the normal random variable with mean mu and variance sigma square. We standardize it by defining a new random variable y given by y is equals to x minus mu by sigma. So generally in questions, we won't be finding directly by using the random variable like normal random variable x. We standardize it first and calculate the required thing. So to standardize any given normal random variable, uh, we can define a new random variable y as x minus mu by sigma, so that now y will be the standard normal random variable and you can solve in terms of y. So the CDF of a normal random variable can be obtained like this. Probability that x less than or equal to x is equal to probability that x minus mu by sigma is less than or equal to x minus mu by sigma. Now, as we define y equal to x minus mu by sigma, it will be probability of y less than or equal to x minus mu by sigma. That is phi of x minus mu by sigma. In the previous slide, we defined right phi of y to be standard normal random variables CDF. So here finally we can find the CDF of normal random variable in terms of standard normal random variable by standardizing it. So we can use standard normal random variable here for obtaining the value of CDF of a normal random variable. So last example, the annual snowfall at a particular geographic location is modeled as a normal random variable with a mean of mu is equals to 60 inches and with a standard deviation of sigma equal to 20 inches. What is the probability that this year's snowfall is at least 80 inches? So sigma is given, mu is given. We need to find probability that x is greater than or equal to 80. So first we'll be standardizing it, and then we'll be converting in terms of standard random variable and calculate using its CDF. Let us look at the solution. The annual snowfall at a okay. Let x be the snow accumulation viewed as a normal random variable, and y equal to x minus 60 by 20 be the corresponding standard normal random variable. So let's assume as usual x to be snow accumulation, which is a normal random variable. Now standardize it by using x minus mu by sigma, which is x minus 60 by 20, and this is the corresponding standard normal random variable. Now we want to find probability that this year's snowfall is at least 80. That means probability that x is greater than or equal to 80. That is nothing but probability 1 minus probability that x less than 80, which is nothing but 1 minus probability that y is less than or equal to 1. That is phi of 1. So it will be 1 minus phi of 1, which is this phi of standard normal random variable CDF values are already known to us. So we can convert in terms of this and calculate. So by using 1 minus phi of 1 value, you'll get it to be 0.7. So this is how you calculate. So that's all. Is a normal and continuous. Okay. Poison. Okay, poison is nothing but so poison random variable is nothing but something which has PDF of this form e power minus lambda into lambda power k by k factorial. So generally how do we apply this is by approximating the binomial PDF which has large value of n and p. So let us take an example. See, if you consider a city and consider a number of car accident to be a random variable. Now, number of cars involved in the accident to be a random variable. Now, number of cars in a city is very large. Now, so n is a large value, and p is the probability that any car is involved in car accident, which is very small. So, in such cases, uh, we can solve it using this PMF by finding lambda equal to NP. Like we can find lambda value as the product of NP, and then by using it, you can construct this PMF and find the required things. That is what Poisson random variable. And exponential is like you will have uh, PDF of this form and just find with the given values you can find whatever required. If you want to find probability that x greater than or equal to 8, just integrate uh, over the given range and you can find the values. Even the normal distribution is similar. If you have this form, then that is normal. If it is given normal now, then you just consider this form and with the given information you can find the required values by integration, or like if they give mean and variance, you can just if it is given as normal random variable, just try to convert it into standard normal random variable by using mean and variance, and then try to calculate whatever required. Is clear now? We don't solve it. I think actually that values will be given to you that was found experimentally. So as we can't integrate whatever we require, we will be converting everything into the standard form. That values will be given to you. Any more doubts? Or else we can end the session. So we can end the session then. There are no doubts.